All right, we have a lot to do today. Just throwing that out there. Are you gonna wine some more?
I didn't do it, I dropped it.
You didn't just drop it. All right. So 6.3 binomial and geometric random variables. There is a lot to do today, so it'll probably take us 2 sessions to get it done. We'll see how it goes as to if I fix it or not, but we'll go through and see what happens. It's not very hard. Most of the work that you do today will be calculator wise. All right. So just understand that. So when the same chance process is repeated several times, we are often interested in whether a particular outcome does or doesn't happen. To test whether someone, here's some examples. To test whether someone has extrasensory perception or ESP, choose one of the 4 cards at random, a star, wave, cross, or circle. Ask the person to identify the card without seeing it. Do this a total of 50 times and see how many cards the person identifies correctly. So we're going to identify the chance process, the outcome of interest, and the random variable. So the chance process, I'm going to do it for the first one, and then I'm going to ask you about the next ones. So the chance process is we're going to choose a card at random. Your outcome of interest is what you want to happen. The person will identify correctly. And then you want to identify your random variable. So we've been working with probabilities of X, Y, Z, whatever we're doing. So we're going to define what that X is. It's going to be, see, it says, see how many cards the person identifies correctly. It's going to be the number of correct identifications. So then if you look at the next one, a shipping company claims that 90% of its shipments arrive on time. To test this claim, take a random sample of 100 shipments made by the company last month and see how many arrived on time. So what's your chance process? And the other one, it was choosing the card. So what are we doing in this one? What are we choosing? Mm-hmm. A random sample. Why? Yeah, but why are we picking a random sample of shipments? And check arrival. And that's your arrival time to see if it's on time or not. What's your outcome of interest? What do we want to happen? We want the shipment to what? Arrive on time. So then I'm just going to call it Y, so it's a different variable than before. What are we counting? The number of on-time shipments. Okay. The next one says, in the game of Pass the Pigs, a player rolls a pair of pig-shaped dice. On each roll, the player earns points according to how the pigs land. If the player gets a pig out in which the 2 pigs land on opposite sides, she loses all points earned in that round and must pass the pigs to the next player. A player can choose to stop rolling at any point during her turn and to keep the points that she has earned before passing the pigs. So what is your chance process? What are we doing? Rolling the pig dice. If we were looking at cards, it would be drawing cards. So what are you doing? What's your outcome of interest? Pig out. And then we're going to use another variable, and I'm going to use variable t. And what are we trying to figure out? Number of rolls until paid out. Good. All right, so some random variables like X and Y in the first two examples above count the number of times the outcome of interest occurs in a fixed number of repetitions. They are called binomial, this is long, random variables. Other random variables like T and pass the pig setting count the number of repetitions of the chance process it takes for the outcome of interest to occur. They are known as geometric random variables. So in this section, we're going to learn the difference between those two. So one more time, binomial is a fixed number. Geometric is not. So like if we were doing cards, a binomial would be draw 10 cards. A geometric would be draw until you get this card. Does that make sense? Okay. So again, we're just working with binomial today. We'll get to geometric later. Binomial settings and binomial random variables. What do the following scenarios have in common? Toss a coin 5 times, count the number of heads. Spin a roulette wheel 8 times, record how many times the ball lands in a red slot. Take a random sample of 100 babies born in U.S. hospitals today and count the number of females. In each case, we're performing repeated trials of the same chance process. The number of trials is fixed. So we already know how many we're going to do. Also, knowing the outcome of one trial tells us nothing about the other outcomes of any other trials. So that means that they are independent. We're interested in the number of times that a specific event, which we'll call a success, occurs. Our chances of getting a success are the same on each trial. When these conditions are met, we have a binomial setting. So what that just set up is with your definition for binomial setting. So to just kind of recap what that said, what we're going to use is called bins. So you guys can see it right there, bins. So a binomial setting arises when we perform several independent trials of the same chance process and record the number of times that a particular outcome occurs. The 4 conditions for a binomial setting are, so you're going to have to be able to tell whether this is a binomial setting or not using this bins, okay? So 3 of them are really cut and dry. When you look at independent, there's not going to be a lot that you can say. One doesn't affect the other. It's basically what it is. So typically the I is a yes or no because you already know what it is. All right, so binary is the possible outcomes can be classified as success or failure. So the possible outcomes are classified as success or fail. So if we're flipping a coin 50 times and we want to get heads, your success is heads. What is your failure? Tails. So that's your binary right there. Success is heads, fail is not heads. All right. Independent. Your trials must be independent. So one doesn't affect the other. So the best way that I can describe this is if you're doing like a deck of cards and you're putting the cards back, we have the same probability, so they don't affect anything. But if we take them out and we do not replace them, then that means that it could affect it. Okay, so watch your independence. The number of trials has to be fixed. So it tells you do this 5 times, do this 100 times, do this 50 times. And then your success has to have the same probability each trial. So we're going to go through in just a minute some examples or some scenarios, and we're going to tell whether they're binary settings or binomial settings or not using bins. All right, so when checking the binary condition, that's your first one. This should say notes. That there can be more than 2 possible outcomes per trial. So a roulette wheel has numbered slots of 3 colors, red, black, and green. If we define success as having the ball land in a red slot, then failure is going to be when it lands in not red, so a black or a green. Think of tossing a coin n times as an example of the binomial setting. Each toss either gives heads or tails. Knowing the outcome of one toss doesn't change, should say change, the probability of a head on any other toss, so the tosses are independent. We talked about that with babies. Just because we had 5 baby girls doesn't mean the next time I'm supposed to have a boy. It's always independent. If we call heads a success, then P is the probability of a head and remains the same. So that probability does not change as long as we use the same coin. So for tossing a fair coin, the probability would be 0.5 because there's 50% chance of getting heads. The number of heads we count is a binomial random variable X. So when we were doing the Jeep tours and we were using X and then we were using C and whatever, those were binomial random variables. X, we're just defining that X is now a binomial random variable. It could be geometric. Remember, we're going to talk about geometric later. So it's not just because it's X, it's because what X is, okay? So the probability distribution of X is called a binomial distribution. Everybody good? Good. All right. To count X of successes, in a binomial setting. This is just that same paragraph reiterated one more time. Is a binomial random variable. The probability distribution of X is a binomial distribution. Again, it's the same thing that we just said in the last paragraph. This is new with parameters N and P, so we're going to define those. N is the number of trials. So if we're doing 50 tosses, N would be 50 of this coin. And P is the probability of a success. So if we wanted heads, our probability would be 0.5. The possible values of X are whole numbers from 0 to N. So if we're doing 10 trials, the possibility would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Later in this section, we'll learn how to assign probabilities to outcomes. And how to find the mean and standard deviation. We're not doing that today. Of a binomial random variable. For now, it's important to be able to distinguish situations in which a binomial distribution does and doesn't apply. So How do we tell if they are a binomial random variable or a binomial distribution? This is when we're going to do Venns. I'm going to rewrite them the first time, but the second time and third time I'm going to use just the letters, the acronym, okay? So remember binary, you're defining your successes and your failures. So the first one, genetics says that children receive genes from each of their parents independently. Each child of a particular set of parents has probability 0.25 of having type O blood. Suppose these parents have 5 children. Let X equal the number of children with type O blood. So what would the success be? Say it again. Type O. What would the failure be? Not type O. The next one is independent. Are these independent? Does one kid having type O determine what the other kid's going to have? No. So one doesn't influence the other. So on this, a lot of times, all you're going to put is whether it's yes or no. You can write it out if you want to, but you don't have to. You're just checking to see yes or no, is it independent? What was your N? Number. And remember, that's your number of trials. Is there a fixed number, yes or no, on this one? Yes. How many children are they having? 5. And again, is it fixed or not? So I'm going to put that in parentheses, fixed or not. If it is not fixed, it fails binomial. Everybody got that? And then the last one, what was your S? It is your success, and it's kind of misleading. What is your probability of success? So what is your P going to be? What's the chance they're going to have type O blood? 0.25. So does this one pass Venns? Yes. So it is a binomial distribution. Okay. So as long as you can fill in all 4, it's a binomial. When you can't fill in one of them, it's automatically a no, and we move on. Okay. Now for these next 2, they may or may not be a binomial distribution, but we're going to go through all 4 letters regardless, just so we can practice what they are. Okay. If you're taking your test, you can stop. All right, so B, shuffle a deck of cards, turn over the first 10 cards, should say 1 at a time. Let Y equal the number of aces you observe. Okay. Can we do a success and a fail? What's your success? What's your fail? Good. So we're good so far. So far, so good. Is it independent? Why? Okay, so here's where some people get confused. Not replacing also affects your probability, right? Okay, so if we pull an ace, what do we suspect is going to happen to the next card? It's probably not going to be, there's a bigger chance that it's not going to be an ace, right? So that's what it means. Make sure that this one doesn't affect the other. So you may just want to keep writing one does affect the other or one does not affect the other when you're doing this, rather than replacement and not replacement, because the replacement is going to change your, or the not replacement is going to change your probability of success. Okay. So then, is there a set number? Yes. So automatically we would have already stopped doing this on our test because it failed. So we would say, no, it's not a binomial distribution. But again, we're just going to keep practicing. So what is your probability of success? Think about this. We're looking for aces. 4 out of 52. Yep. Now, if we pulled an ace out the first time, what would my probability be the next time? 3 out of 51. So it changes that probability. Okay. All right, let's look at C. So this one would not be a binomial.
For the probability on the last one, can you just put the 4 out of 52 in instead of keeping the one, like the 3 out of 51, 2 out of,
I wouldn't put that part at all. I just put this.
stop there.
I would honestly just stop when you got here because the only question they're going to ask is it binomial or not? Eventually, what you're going to do is do a bigger problem and you're going to test bins before you move on to the next part. It will always work when you're doing those. Okay. All right. Part C. Shuffle a deck of cards, turn over the top card, put the card back in the deck and shuffle again. Repeat this process until you get an ace. Let W equal the number of cards required. All right. Is it binary? What's our success? What's our fail? Yeah. Is it independent? Yes. One doesn't matter because we're putting it back in there and then we're shuffling it again. So we have the same look each time. Okay. What about your number? No fixed set, right? What are we doing? We're drawing until we get one. Okay, there's no set number. We're trying to get an ace, so what's the probability? 4 out of 52. And again, this one would be not binomial and because it doesn't pass the N in bins. But the first one was, because it passed everything.
On your test, do you have to write out all your steps just like that without even showing the words?
Now, this would probably be more of a multiple choice, or it may ask you to, but on my test, it would not. I'm telling you, when you do the bins, you're going to do more work. You're not just going to do bins and be done. But it might ask you, like it might be a multiple choice where it says, is it a binomial distribution? And A may say no, because it doesn't pass the independence. No, because it's not a fixed number trial, whatever. So you're not going to have to do like write it all out all the time. You just have to know what the 4 mean. All right. Part C of the example raises an important point about binomial random variables. Besides checking the bins, make sure that you're being asked to count the number of successes in a certain number of trials. In part C, you're asked to count the number of trials until you get a success. This can't be a binomial random variable. So now we're going to go through these again, and we're going to determine whether it's a binomial distribution. So again, if they ask you about a binomial distribution, that's your bins. Okay, so we're going to start with number 1. It's the same thing that we just did, okay? Just more practice with it. Shuffle a deck of cards, turn over the top card, put the card back in the deck and shuffle again. Repeat the process 10 times. Let X equal the number of aces you observe. So is it binary? What's your success? What's your fail? Not ace. Is it independent? Again, one doesn't depend on the other. One outcome doesn't affect the other. Do we have a fixed number? What is that fixed number? We're doing 10. Do we have probability of success? 4 out of 52 because it's the ace again. So this one is binomial. Two. Choose students at random from your class. I don't like this example because they actually want you to use your class. And right now we don't really have a class. Okay. So let Y equal the number who are over 6 feet tall. So what's your success? Over 6 feet. What's your fail? Yep, not over 6 feet. All right, what about independent? Think about it.
Because you take one person. And
Yes, you take one person out and then you take another one. So it is not independent. So it would fail there. So we already know it's not binomial, but we're going to keep working on it. All right. What about a number?
Yeah, there's a fixed number.
There would be. I'm gonna say on this one, there's not because it doesn't ask you to. That's why I don't like this. That's the one part that I don't like about this question. And with us not being in class, it makes it really weird too. So I'm gonna say no set number.
I'm not homeless students,
I don't think they'll ask about your class. I think they'll tell you a specific class of 20 students or something.
I mean, like, on the Instagram, they're all in like the video.
I would just to practice it because you're gonna have to do, like I said, you're gonna have to do it eventually anyway. So just get used to it. And then, do you have a probability of success? Will you? Yes, because you're gonna have whatever our class is. So I think we're down to 20 now. So it's like 1 out of 20 or 3 out of 20. How many ever 6 feet tall we have? That's what it's gonna be. So this would be a yes, but it doesn't matter in this case because we've already failed on the independence. Right? So again, I just don't like that question. I might change it one day. Roll a fair die 100 times. Sometime during the 100 rolls, one corner of the die chips off. Let W equal the number of 5s you roll. What's your success? What's your fail? Is it independent? Does one roll affect the other? Nothing affects it, so it is independent. Do we have a set number?
Yeah, 100.
Is the probability going to be the same every time?
Yep.
Think about it. What's the one piece of information they gave you?
Oh, one corner chip.
Yeah, so if that corner chips off, it's more likely to roll towards that corner or stop or something like that. So the success would not be the same. The probability of success would not be the same because of the chipped die. All right. When we get to the next check your understanding, we're done, but it's a long way away. Just forewarning you. This is the more mathematical part, okay? So all that was just checking the bins. Now we're actually going to do the math for it. So in a binomial setting, we can define a random variable, say x, as the number of successes in independent trials in independent. What's the probability distribution of x? Let's see if an example can help shed some light on the question. So each child of a particular set of parents has a probability of 0.25 of getting type O blood. Genetics says that children receive genes from each of their parents independently. So there's your independence. You guys see that? If these parents have 5 children, the count X of children with type O blood is a binomial random variable with N equals 5 trials and a probability of 0.25 of success on each trial. In this setting, a child with type O blood is a success, which is S, and a child with another blood type is a failure, an F. So we'll get this one done and then we'll switch out. What's the probability that X equals 0? So the number of children they have that have they won't any of them have type O blood. So that is, what's the probability that none of the 5 children has type O blood? It's the chance that all 5 children don't have type O blood. The probability that any one of these couple's children doesn't have type O blood is 1 minus 0.25 or 0.75. So a success is 25%, so a failure would have to be 75%. Got it? That's all that's saying. By the multiplication rule for independence events, so that means child 1 and child 2 and child 3 is multiplied. So remember, anytime we say and, we're going to multiply. So the probability of getting 0 is the probability I have failure after failure after failure after failure. The probability of failures is 0.75, and the multiplication rule says we just multiply that together. What's another way I could write this? Perfect. That's going to come in handy in a few minutes. And then when I put that in my calculator, I get 0.2373. So there's about a 24% chance that all kids will not have type O blood. Okay, so make sure you know how to define that too. How about one kid having type O blood? There are several different ways in which exactly one of the 5 children would have type O blood. For instance, Joseph Patterson. For instance, the first child born might have type O blood while the remaining 4 children don't have type O blood. The probability that this happens is, so if we have the probability that the first one does, but the other 4 do not,
Would it like always define it like that, and not guess which of the children are gonna have it?
right now, no. So what's the probability of a success? And then there's 4 failures. So another way to write this is 0.25 times 0.75 to the 4th. And then I kind of skipped a line out of here. There's actually 4 more possibilities to consider. You're just moving that S down the line. So the first one would be a failure. The second will be a success. The rest are failures. The third kid will be a success. The rest are failures. The fourth will be a success, and the fifth. So it looks like this. Fail, success, fail, fail, fail. Fail, fail, success, fail, fail. Fail, 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 success, fail. And then the last one is a success. Every one of these probabilities are going to be the same thing that we just did. There's 1 success and 4 failures. So in all, there are 5 different ways in which exactly one child could have type O blood, each with the same probability of occurring. As a result, this is how we would write it. The probability of getting 1 success is the probability that exactly 1 child is type O. There are 5 chances of exactly 1 happening. And their probability is 1 success and 4 failures. Which gives 0.39551. Which means there's about a 40% chance of exactly 1 of the 5 children having type O blood. Now, realize that we're going to get to a point where like it's not easy to list them out, and that'll be just in a few minutes. And they have a formula that you use to figure that out. So if you didn't want to write all of these out, trying to figure out what that 5 is, there's an easier way. Okay, got it? All right, I'm going to go out of this, stop sharing, stop recording.